First of all, problem set 4 was sent to you, and in there is a midterm announcement. Further details will be sent to you in due course. So please stay tuned and pay attention. So last time, we tried to emphasize that we are handling a new class of problems. Here we are doing time-dependent Hamiltonian problems. Why? Because when we handle light in a classical way, it is something like a Yee field oscillating in time. So there will be explicitly time-dependent in the interaction term. We were trying to write down a formal interaction term so that we have a context to go with when we discuss the more formal approach. This is the electric dipole mechanism. That will be the most important mechanism in light absorption, emission from an atom. It has to do with the electric dipole moment. There's an electron in the atom, actually many electrons in the atom, but for simplicity, we imagine that we are handling one electron. So we have one electron charge minus E. At some location with a position vector R, the center is the nucleus. Therefore, by definition of electromagnetic context, the electric dipole moment is the charge multiplied into its location. So minus ER is formally the electric dipole moment. You can find this expression in, for example, Griffin's standard electrodynamics textbook. In quantum mechanics, we need an interaction energy to go into the Hamiltonian. But that's easy. Electric dipole interacts with electric field. And there is an oscillating electric field in the incident light, which is EM waves, as you know well. Therefore, in one step, we know an energy, which is minus mu dot into this script E I used to represent the electric field. Because we have used some capital E for energy of the atom, that's why I use this script V E to avoid confusions. So let's write it down explicitly. The E field in a EM wave has the form of, for example, a simple form. It is a vector and it is oscillating. So that will be a wave, a traveling waveform in the K direction, right? And the electric field has an amplitude pointing at some direction specified by the vector sign. In the easiest way to think about it, we may think about linear polarized electric field. That is to say, the electric field is always along a direction that I call Z, and thereby the propagation direction must be perpendicular to it, that we call X. That is just arbitrary assigning the direction. So this is the incident direction, then I call it X, and then the E field is perpendicular to it, going bigger, smaller, zero, negative, and then oscillating, and that I call Z. That is linearly polarized light. We mentioned one piece of important physics in doing this light-atom interaction. The point is that the EM wave has a wavelength. Think about light, visible. So it is 500 nanometers or so in wavelength. But for the dimension, how big is an atom? It is about 1 angstrom, which is 0.1 nanometer. So this is 1,000 times bigger than the size of an atom. The physical implication is that over the size of an atom, the E field, no matter which part it is, okay, will not change by much. That is to say, over 1 angstrom, the E field is a constant over that range. By that we mean we can ignore this kx part because x is the location of the electron, that is to say, it goes through the dimension of the atom, and k is 2 pi over lambda, which is 1 over the wavelength. Therefore, a over lambda, that is to say kx, is much less than 1, and we can ignore it, approximate it to 0. The nice thing is that we don't need to worry about any spatial thing in the field and focus on the time part, the omega part of the field. With this simplification, the E field becomes a very simple thing: linear polarized, a vector and amplitude in front, and then cosine omega t. If it is linear polarized in the Z direction, this amplitude points in the Z direction with an amplitude, okay? So this will be the simplest form, although not completely general. This is more general, okay? So, but from time to time, we will go back to the slightly more general form, but this is easier to follow all the physics. Therefore, we have the perturbation term, which is time dependent. It is the E field that interacts with the electric field. It's the electric dipole moment that interacts with the E field. So it is minus mu, this is matter, the atom, dot into the field. This is light. That is why the whole module takes on the title of light matter interaction. And that is a big part of physics. If you let an atom sit there forever, you don't know anything about it. You need to prop it. You prop it. One convenient way is to do spectroscopy. 光谱學, 光譜學. So you shine a light, see what happened. And this is the focus of our discussion in this module. So this is the general form. And then tuck in the electric dipole moment is minus ER, therefore we pick up E times R and then dot into the field. So 7 is still quite general. But if we only consider linear polarized light, this dot product can be easily carried out. Position dot into the Z unit vector means you will pick up the Z coordinate, the Z position of the electron. Again, this is matter, this is light, okay? So all the way you see matter-light interaction. So 7 and 8 will be often referred to in the following discussions. So let's summarize what is the problem in our hands. It is an atom. The part that you solve in the last term for hydrogen and earlier we put in some perturbation, but those perturbations are time independent. The new element here is that we have the atom with the light coming in. We have an interaction term that is time dependent. So that is the new problem. Explicitly, we have time. Actually, I should have said this perturbation is also related to Z or R and T. But because T is the new element, I write down this is a function of T explicitly, but hidden behind there is a position of the electron in the H prime. What is the question? We have a time-dependent Hamiltonian, therefore, we will not ask for energy eigenstate. That doesn't make any physical sense, right? Because the energy is not conserved in a time-dependent Hamiltonian. So we give up on that question. We don't ask that question. We ask another question. We always focus our question back on this atomic part. That is time independent. So we know there are energy eigenstate of the atom, meaning 1s, 2s, 2p, 3s, 3p, things like that. Then we ask, if you are given an initial condition, for example, the atom initially is at 2p, then I start the light incidence at some time called time equals 0. That 0 is arbitrary set. The beginning of the perturbation comes in. Then I will ask, what is the probability of finding the atom to be in some other state? Not in the initial state, but in some other state that I call the final state, after some time t, that the light has started working. Okay, so always remind yourself of the question in hand. This is the question. It is an initial value problem, that is to say, given initial state, the perturbations start at time equals 0, wait for a while, time t, afterwards, what is the probability of finding the atom to be in some other states? That is to say, what is the probability that transitions have been made? Okay, so that is the question. So is the question defined clearly? Do you understand the question? Okay. Any question about the question? Okay. Now, at this point, if you understand the question, then what follows? There are things that if you find it too complicated, never mind. I will kill you as, well, I will signal you at some point. This is the key answer to this question, okay? And then you can grab that answer and analyze what does that answer tell you about transition probabilities, all right? But from this point to that point, there are some general quantum mechanics theory to learn, okay? It is the time-dependent perturbation theory. In our course, I don't really mean to introduce the whole formalism, but I will give you the correct big picture and all the key steps so that the end result will look very reasonable. And then from that point on, we can analyze what is stimulated absorption, what is stimulated emission, and what is the rate for that to happen, why Einstein says something about them. They are equal rate, okay? So that will be the storyline of our discussion, okay? So at this point, if you understand the question, you are in good shape. So pictorially, the question is such. Initially, the atom in initial state, that is referring to the atom eigenstate. Then this thing comes in. The full Hamiltonian becomes the atom with something else, the interaction. Then this state, initial state, should evolve in time, but in a rather different way if you only have the atomic part of the Hamiltonian. Then this evolution at time t, you ask, any chance to find the atom to be in a different state called final state, okay? Now, the first picture is that if this part is not there, for example, we don't switch on the light, then it is easy. If it is in an eigenstate phi I initially, it will be 100% in the initial state I at time t later. Okay, so do you understand this point? Because it is an energy eigenstate, all right? Now, by logic, it means the following. Any transition to some other state must be due to this light matter interaction term, right? Because the logic is, if it were not there, the state will, the eigenstate will stay forever, okay? So that is another concept to keep in mind. So far, so good, all right? Get that point? Get that point? So with this, then we can start thinking about what to do next, okay? Now, for those of you who don't like formulas, take this picture with you. What we are asking is equivalent to the following problem. Easier to think about. I pretend my 1D particle in an infinite well as an atom. Well, that's reasonable, right? Because you know there are discrete states that looks like an S and a P, things like that, right? That makes sense, at least. Now, initially, if it is in the ground state, so before time equals 0, you have this atom given in the ground state. Now, you have a sinusoidal oscillating cosine omega t interaction. So pictorially, it is equivalent to, you have an infinite well at the bottom, it is oscillating. Okay, so carry this picture with you. That is the kind of problem we are asking. The question is then, after some time t, given the system was in ground state at the beginning before it shakes, will there be any chance you find that this infinite well has, you find it to be in a first excited state or second excited state, okay? So that is exactly the question. Then let's see whether it is possible. So here, it is important concept number 2. It is possible and rather easy to understand. Now, for example, if you think about an instant t greater than 0, the well is shaded to this point, okay? And maybe at this point, we turn it off. We turn the perturbation off, stay there, okay? So now, let's see. What is the ground state of this tilted well? I think you have done this in your perturbation part, right? The early part. Well, by physical sense, this part has a lower potential energy, thereby, by having more chance to find the particle on this part, the wave function will have a lower energy expectation value. So by this simple sense, the ground state should tilt it a bit to the left-hand side. I try to exaggerate the point a bit here, just to make sure that you know what I'm trying to draw, okay? So guys, do you understand what I'm drawing? I'm drawing the ground state of the tilted well. That is the perturbed flat bottom atom. Do you follow me? Questions? Is that okay? Now, then we ask, if you are given this, what is the probability that the original atom, that is to say, this dashed line flat bottom atom, if we look at the atom, what will there be a chance that you can find it in the first excited state? Now, remember that such a wave function confined in this well can always be expanded in terms of the energy eigenstate of the flat bottom well, the atom. So we have some coefficient times the ground state, some coefficient times the first excited state, and we should have more terms. But for simplicity, I focus on this excited state. Now, even by eyes, if I add this into here, the positive part add to positive part will be more positive. That is to say, the sum will be tilted to the left side as we wanted it to be. All right? On the right-hand side, it is positive in one term and negative in the other term. If I tune this properly, the weighting, then I could have a smaller tail on the right-hand side. Let me conclude, that is to say, at this instant tilted well, the ground state is a linear combination of the ground state and the first excited state of the original atom. That is to say, through a perturbation, even the atom was initially 100% in the ground state, at some later time, it is a probability A2 square that you can find it in the first excited state. A transition has occurred. Okay, big picture, do you follow? Is that okay? Then our task will be to look for formulas, quantum mechanics formulas for A2T square. Okay? So that will be our goal. Okay? Rather difficult thing to do, but at least you know what to do, right? Given at ground state, now I want the excited state probability. So I need the amplitude A2T and square it. That is all we want to do, okay? And even worse, we will be very humble just to look for what is called the lowest order approximation. Okay, just like what we did in perturbation, we had the first order perturbation. If that result is meaningful, we will be very happy, and then we don't do any second order, okay? So that is the strategy. Next, I will introduce you so-called what I call the poor man's time-dependent perturbation theory. That is to say, it's very rough, not rigorous. I will first introduce this picture, and then I will go to the appendix that will give you a fuller, accurate description, okay? So get the big picture, very rough one. Nonetheless, the end result will be the most important, okay? So now pay attention. slightly more mathematical, but if you have the question in mind, you know what we are looking for, shaking, oscillating a bottom of a well, look for the excited state probability, then you should be able to follow what's happening. Okay, so in quantum mechanics, in handling time-dependent problems, you only have one equation. Isn't that simple? In doing E and M, you have 4 equations to pick, right? Troublesome. But in quantum mechanics, time-dependent problem, time-dependent Schrodinger equation. That's it, nothing else. So that is easy. So always go back to this equation, okay? Then the question is, if you are given the initial state, that is to say, phi position function x, for simplicity, just 1D, okay? So very rough, but at time equals 0. Then the question is, what is it at a later time? I don't even care about later long time, just a little bit delta t later, okay? This h is the full Hamiltonian of the problem. In our context, before time 0, so negative time, it is the atom only. After t equals 0, it is the full Hamiltonian with the interaction part. So let's think about it as the full Hamiltonian with the interaction part. Now, let's do Taylor expansion, okay? Now, because this is not far away from 0, so formally it is no change, 0 order, then first order will be d phi dt times a little bit of time, okay? So the first line is Taylor expansion of the wave function itself, okay? So first line, okay, right? Now, we see this derivative can be expressed using the time-dependent Schrodinger equation. This is 1 over IH bar H phi, okay? So I plug it into here, okay? Still okay, right? Now, just to remind you, in our context, before time equals 0, atom only, starting at that point, we switch on the whole thing with interaction, okay? Therefore, the H that we see at time equals 0 has just switched on, we have this part, okay? Therefore, we started to see the action of H prime. Let me remind you, if this part were not here, as we already discussed, it will stay on the initial state forever, okay? If this is an eigenstate. That is to say, the atom part will not take it to somewhere else usually, right? Then it must be this part that operates on the initial state, an eigenstate of the atom, that will take it to some other, that will create a new state, right? An initial state of the atom, an operator on it generally will be some state, but not necessarily an eigenstate of the atom. It will take it to some wave function, that is to say, okay? So, all in all, you see the following form, all right? This is the crucial part. This will be some wave function at time delta t. Now, if I want to look at what is the chance of finding the atom to be in some final state, what should I do? I should project that new wave function, okay, evolved it a little bit, but this part is the crucial one. I have a new wave function. I want to find, is there a component of final state there? Okay, then I pick that final state eigenfunction and project it onto the wave function. Okay, do you understand this particular step? Any question? For this step, I am looking for A, F, delta T, the coefficient that goes in front of phi F. If I expand this thing in terms of all the eigenstate, okay? So that will be AF delta T, the probability amplitude, okay? Now, then, if I do this on this line, the first term vanishes because eigenstate of the atom are orthogonal, okay? Now, even this term add on this will give us an eigenvalue, which is a real number, and then phi I. This again will be 0. Therefore, as I emphasize, it is the perturbation that can take the initial state to some other states. And that some other state may have a little bit of chance for the atom to be found in the final state. Okay? So let me summarize. With this very brief, very rough discussion, we have found one integral that is crucial in determining whether there will be a chance that the atom in initial state can be found in the final state at a later time. Okay? Now remember, so I'm jumping ahead a little bit. The form now is final state, initial state, okay, with an integral over all space. Remember, in H prime, there is an Z for the electron, okay? So if I put in a Z here, okay? Now, you see there is an integral, okay? For example, initial is hydrogen 2p, so you look up the wave function, plug it in. Final is hydrogen 1s, it is going down, okay? Or well, going up 3s, okay? So you look up, put it there. In between, you put in an Z. Z is R cosine theta, all right? Then you have an integral to do. Okay, do you follow me? I'm okay. Hello, any question? Is that okay? All right. Now, punchline follows, okay? I usually pause before I give you another concept. Now, if this integral turns out to be 0, now that has to do with 2p, 3s wave function, and a x or y or z in between, okay? If that is 0, that is to say, you cannot find it there. There's no chance for that transition. You have heard about selection rules, right? I mentioned selection rules. Some rules are delta M must be something that is the same, right? That is the consequence of this kind of integrals. Okay? That's it. You already, kill one bird, okay? Already there, all right? The second thing that is not quite clear at this point is, why do we need the incident light to be of the right h bar omega? of that energy difference, okay? Let me tell you, it is also in here, but because of that we are doing a very rough treatment at this point, it is harder to see it from this here, okay? When we go to the fuller, the more complete treatment, we kill two birds in one formula, okay? You have both selection rule as well as the energy criteria all in one line. Very, very neat, very beautiful formula, all right? So that will be the physics that you see. But at this point, don't worry. The point now is that even that simple idea, an initial state, you must use the perturbation to take it out to somewhere else. Then you can look for the probability of finding the atom in some other final states, and it is governed by an integral like this. Okay, big concept here, but not very very precise, but do you get the big concept? Any questions? Okay, now let me now give you the punchline formula, okay? Of course, by doing this kind of Taylor expansion, the method is kind of cheap. You cannot get the full complete formula, but we get 80% of it. So let me just introduce the key formula at this point. If we do all the mathematics accurately, then we will have equation 13. Now let me motivate equation 13 and at least make it plausible, okay? Meaning it makes sense, okay? It makes good sense. So we already see that if it is not here, it will stay there at the same state forever at later time t prime, okay? So I consider some t prime after t equals 0, okay? So if it is not there, it already itself will evolve it with its own phase. Now that is the atom part. But atom part is always there. Therefore, we think about it as the initial state will evolve to some time t prime. And at that point, this interaction works, okay? Therefore, we expect this to take the state out from phi I and mix in some other states. We assume that interaction start at t prime over a small interval delta t prime. So that is the place in our previous discussion. This generates a new wave functions, inside which there's still some chance to find it at the initial state, but there are chances to find the system in some other final states. How much? Then we project the final states, but now include a time evolution factor due to atom part alone before we do the projection, because we are playing at time t prime, okay? So therefore, that integral we saw is now written as some particular time t prime. Nothing very profound, but we just think about a t prime, an instant from 0 to t. Now, we are asking the question at time t. From 0, switch on, time t, we ask question. We are thinking about somewhere in between called t prime at little delta interval delta t prime next to t prime, okay? So this spatial integral is a generalization of the thing that we just discussed. That is a interval next to time 0. But now we generalize it to a time interval at some t prime that is an arbitrary time between 0 and t, all right? I think on your side, from 0 to t, okay? This is t prime, okay? All right, now, but the question we want to ask is the probability of finding the system to be at some other state f at time t. That is to say, time t after the perturbation acts on the atom. So we must add the effects bit by bit together. Therefore, we have an integral over time so that we account for the fact that the perturbation has been acting on the atom from time 0 to time t, all right? Now, this is equation 13. I try to convince you that that makes sense, all right? Of course, words cannot do justice, 100% justice to this formula. We need the derivation. I will do it for you in the appendix. But for the moment, for those who don't like derivation at all, fine. Grab this equation and then you will see wonderful things come out. You will see selection rules, you will see energy criteria, and what's more wonderful is that from one equation alone, this equation alone, you will see two processes. That's rather fascinating. Two processes coming from one same equation. The processes are absorption. The initial state is lower, the final state is of higher energy. But the same equation, you also see stimulated emission. The initial state is actually higher, the final state is actually of lower energy. It is all in one single equation, number 13. Okay? So, if you want to skip derivation, fine. Try to convince you that equation 13 makes sense, and then go for lunch for a while and then come back, and then there will be some point that we will pick up equation 13 and discuss its consequences. Okay? So, but it makes sense. Now, I just mentioned that for our poor man's way, we don't see the energy criteria, but now we can see it now. We have a final, we have an initial. Do you see that there is a final minus initial energy already, right? Remember, there is a cosine omega t in here, okay? Cosine omega t is exponential I omega t plus E minus I omega t over 2, right? You have three exponentials. When you do the time integral, that will give you the energy criteria. Bravo, isn't it? Okay, everything comes out nicely. So a lot of things. So finally, I already hinted at that. That equation works. I'm just calling this initial, I'm calling it final. I haven't mentioned anything that the final should be of higher energy or of lower energy than the initial. That is to say, 13 works both ways, general, okay? So that is the poor man's way, okay? There will be an appendix A I will do after the break. And then the next part, the formal part, okay? Page 23. The starting point will be, I pick up this equation and start working out the consequences in the context of atomic transitions, okay? So The next section after the break may be slightly mathematical, more formula, but that is another approximation methods that I would like to introduce in the course. So it should be cross-referenced to the approximation method module as well. Okay, so let's take a break now, and then I will resume in about 8 minutes. All right.